Bien. Eh ben, bonjour, mesdames et messieurs. So before beginning the defense in English, let me introduce the jury. So first of all, Jérôme Bosch, who is a professor of automatic at University of Picardy, on the right. Mr. Carlos Astorga, who is a professor at Instituto Tecnológico de México by Visio. Hello, Professor Astorga, can you hear us? I hope so. Yes. Professor Astorga, can you hear us? And tell something, maybe?
He was here just before.
Okay.
I think he lost connection or something like that.
Okay. Hello. Next, Professor Ascension, Zafra Gabeza, who is professor at University of Sevilla, on my left. Mr. Jan-Erik Bouffard-Vercelli, who is a doctor from Schneider Electric, in Visio also, yes. And myself, so Delphine Rieu, I am professor at University of Grenoble, and of course your supervisors, so Lionel Vecchiu and Adriana Aguilera Gonzalez from Estia. So you will have about 45 minutes to make a short synthesis of your work, okay? And after we will have a discussion, okay?
Thank you. You can keep it, please. It's okay? So, good afternoon, esteemed jury member, dear supervisor, colleague, and friend. Thank you for attending my thesis defense. It's a great pleasure to present my work entitled Advanced Strategy for Online Monitoring, Fault Identification, and the Diagnosis in PV System. This research work was done in Estia under the supervision of Lionel Vecchiu and Adriana Aguilera Gonzalez, with the aim of improving the reliability and dependability of the PV system. Sorry. So to give you a clear overview, this talk is organized into five main points. Firstly, it introduces the context and objectives. Then it defined the limitation, research challenge, and research gap in the current literature. Then it will introduce the monitoring model and the diagnosis strategy developed during this PhD thesis. At the end, it concludes with the main conclusion and perspectives. So, as you know, PV system represent an alternative, sustainable, and green technology to replace the depleted conventional fossil fuel. It gains significant attention due to several merits, such as maturity, universal availability, scalability, longevity up to 30 years with the new technology, and minimal maintenance and operational cost. As such, the PV system installed capacity has increased exponentially, surpassing wind energy for the first time in history. Again. Surpassing wind energy for the first time in history in 2022. As shown on the right side figure, in 2022, it reached more than 1.3 gigawatt hour. This is mainly due to two main factors. falling of average PV cell prices, as seen on the left side, and accompanied with the supporting policies. It's expected to reach more than 9 gigawatt hour at the end of 2030 through technical improvement in reliability and PV service lifetime. However, the proliferation of PV system into microgrid pose new challenges, mainly concerning resiliency and stability. Despite that PV system require low maintenance due to the absence of moving part, they are still vulnerable to certain kind of fault during their life cycle. As shown by the bus curve, fault can appear at the early stage fault due mainly improper installation and transportation, wear-in, and material corrosion. At their mid of life, PV systems are subjected to unpredicted fault with random failure rate, mainly due to environmental factor and operational strains. At the end of their life, PV system can experience an exponential failure rate, mainly due to wear out and material corrosion. This fault, in fact, can drastically degrade the performance of the PV system, resulting in a huge financial and power losses, or even can turn into catastrophic failure, jeopardizing the safety risk of the PV system, endanger human, animals, and equipment. So it's paramount to continuously monitor the PV health status in order to timely detect and identify fault in the PV system before escalating into failure. The main objective is to avert safety losses, reduce maintenance costs, thus maximizing return of investment. This element can contribute to a proactive maintenance policies, ensuring resiliency and dependability of the PV system by satisfying certain diagnosis criteria, such as quick detection and identification, adaptability, generality, through the design and intelligent FDD systems that balance robustness and computational cost. To achieve this objective, a systematic literature review was conducted. It was structured into 4 main parts. Firstly, it addressed the risk analysis to identify the different type of fault in the PV system, their mode, their effects, their frequency of occurrence, and their potential pathways. Once these critical faults are selected for examination, the next step is to identify the suitable FDD approach and algorithm to fill the gap in the existing research literature. So, as you know, fault in PV system can manifest in almost any part. According to their locations, they can be distributed on the AC or DC side. AC side fault mainly include inverter fault, its auxiliary controller, and a grid interaction abnormality. However, this kind of fault, according to the risk analysis review, can be usually detected and isolated using conventional protection system. On the other side, fault on the PV array side, according again to the risk analysis review, can exert the most significant impact on both safety and performance. Even though the PV system, according to some standards, should be equipped with protection system like circuit breaker, fuses, RCD, AFDI, this protection system fail to detect and isolate the fault. According to the table on the top, we can show that these protection systems failed recently in 2022, 2020, and 2023, leading to fire hazard on the PV system. This shortcoming is mainly attributed to the non-linear behavior of the power voltage characteristic and the no uniform irradiation on the entire PV array. And fault, in fact, occurring at low irradiation level remain undetected due to low power generation. These faults remain below the breaking capacities of circuit breaker. Fault in PV array, according to the fault tree analysis, can be classified according to their nature and causality as aging degradation, represented by potential-induced degradation and light-induced degradation, or physical fault, such as cell crack, glass breakage, junction box detachment. Environment fault can cause either temporary due to dust accumulation or permanent effect as seen by the circle, like hotspot and lightning. On the other side, electrical fault can be broadly classified as DC cable fault, connection box fault, and the blocking diode fault. This fault can exert distinct time behavior. It can be categorized as abrupt, incipient, or intermittent fault. For example, mismatch faults such PID, potential induced degradation, LID, can cause an incipient effect on the power performance. On the other hand, seen by the red rectangle, electrical faults such as line-to-line, line-to-ground fault can exert abrupt effect on the power losses. However, the classification of this fault remain coarse in the literature because the fault in PV system can meet multiple characteristics. It depends on their location, their severity, their magnitude, and the portion of the PV cell model affected by this fault. At the same time, can attain many safety risk levels, such no impact on safety, like junction box detachment, or direct fire hazard, such as arc fault and lightning. Actually, the fault in the PV system can stem from a combination of factors, like internal or external factor. These can lead to a mismatch fault, which induce in turn an elevated temperature and non-uniform temperature, leading to certain type of fault in the PV system, and non-uniform degradation and power losses. These faults actually can create a closed loop mechanism, either aggravating the initial cause or initiating another type of fault which can be catastrophic. So even a minor fault in PV system can trigger a domino effect or catastrophic failure. According to the risk analysis review, based on their frequency of occurrence, their magnitude, their severity, and their effect on both performance and safety, some categories are taken into consideration, mainly encompassing electrical fault, which is in red, mismatch fault, and abnormal degradation. These faults are modeled at model level, string level, and array level. For example, if we take electrical fault, which is mainly represented by open circuit and short circuit fault. At the array level, it's represented by F01, modeled as a resistance in series, which describe a PV cable disconnection or wire losing or blocking diode abnormal behavior. On the model side, as seen by the zoomed figure on the left, it's labeled by F07, as well by its resistance in series, and describe soldering failure, cell crack, and disconnection wire. For mismatch, it's mainly represented by F06, which describe a partial shading on the PV system, and it's modeled on the string side and the model side, and modeled by, again, multiply the irradiation level. For abnormal degradation, it mainly, given the cause-effect relationship between mismatch fault and abnormal degradation, it's mainly represented by shunt degradation, which reflect the PID, potential induced degradation, and series resistance, which either on the array side describe the natural aging, and on the model side describe burn mark, EVA discoloration, and delamination. Once the critical faults are selected for examination, the next stage is to identify the suitable FDD approach. Actually, the FDD approach in PV system can be broadly classified into visual inspection to detect visible defect and obvious damage, and image analysis technique. Image analysis technique can either be performed manually using a handheld camera or more advanced strategy using a drone. This can be classified into visible image, also to detect visible fault, or more advanced strategy like thermography and luminescence based on the analysis of discrepancy in thermal behavior or radiative recombination. On the other hand, we can see that electrical measurement has gained recently an outstanding popularity that are based on the analysis of the waveform of the signal to detect fault. They can be broadly classified into signal analysis, IV curve analysis, which is a popular method, as the IV curve contain rich information about the health status of the PV system by analyzing the I short circuit, the V open circuit, the current slope, the voltage slope. Certain fault can be detected in the PV system. On the other hand, MPP measurement can be regarded as a subset of the IV curve by analyzing only the voltage, power, and current at maximum power point. The literature review analysis allow to create a qualitative comparison to identify the strength and limitation of each method. The comparison is based on two criteria: computational charge and the diagnosis performance. Considering the computational charge, it's obvious that visual inspection is the simplest and cost-effective method. However, this method requires human intervention to detect only visible fault in the PV system. On the other hand, we can see that MPP measurement, it's a competitive approach. It's based only on the analysis of the MPP point. It's cost-effective method. It leverages existing sensor already used for protection devices and MPPT measurement, avoid the need for additional hardware to detect and identify fault. This method actually can be continuously performed at any irradiation and temperature level without the need for power interruption, as it's the case for imaging or IV curve analysis. Depending on these criteria, we can see the MPP measurement stand out as an effective and simple solution. On the other hand, regarding diagnosis performance, we can see that the MPP measurement is actually suitable for large-scale PV system and affordable by small-scale PV system. It can detect quickly fault on the PV array and ensures the detection of incipient fault. However, regarding generality, imaging technique can reveal a broader range of invisible fault, but require additional equipment. As a trade-off between computational charge and the diagnosis performance, it's evident that the MPP measurement stand out as the most effective technique to tackle the challenge in the PV system. Once the FDD approach is selected, now we delve into the best FDD method. Actually, the FDD method in PV system can be broadly classified into data-driven, knowledge-based, signal-based, model-based, and hybrid method. The comparison allows to identify the limitation and the strengths of each method. It's obvious there is no method stand out as the optimal solution for all diagnosis issue. Each own its limitation and the strengths. The selection criteria depends on many factors: the availability of the data, the availability of mathematical model or physical model, their complexity, the level of experience and expertise, and the presence or not of noises and disturbance. For example, signal analysis ensure fast detection capability, well suited for a system with limited input data, but it's prone to noises. On the other hand, knowledge-based method offer high interpretability level. It involves operator in the decision-making process, but it's less its effectiveness in complex system. And especially in such complex system and the stochastic system, faults are beyond the experience and expertise of engineers and operator. On the other hand, we can see model-based method. If well-established mathematical and physical model is at the hand, it provides robustness against perturbation and noises. However, its effectiveness depends on the accuracy of this model. For data-driven model, we can see if a large amount of data set already exists, they can offer a fine granularity level of classification and ensure the detection of incipient fault. At the end, the hybrid method can combine the complementary strengths of many models to achieve a higher fault detection accuracy and the classification. However, it increases system complexity. Their combination requires careful design. Before selecting the suitable FDD approach, it's worth acknowledging the research gap in the existing literature. By analyzing the state of the art, we found out that the most of the FDD scheme overlooks the system behavior at low irradiation level, where the power voltage become highly nonlinear and the fault remain undetected due to low power dissipation. They do not account for measurement noise, neither take into account the MPPT effect that mask the fault by trying to maximize always the maximum power point, and they require additional hardware. To tackle this issue, we developed a new FDD framework based on MPP measurement without sensor irradiation that covered the whole irradiation scope. We introduced two FDD strategy, a hybrid strategy that combines the statistical data-driven model with a model based to restrain measurement noises and a knowledge-based method based on the physical behavior of the PV system at each type of fault. On the other hand, a data-driven strategies that are mainly based on machine learning to extend the granularity of fault classification to model, array, and string level. To achieve a robust diagnosis strategy, it's paramount to design a reliable monitoring model in this and over. For so, we propose actually 4 monitoring models based on MPP measurement without irradiation sensor, 2 statistical monitoring model, and 2 data-driven machine learning monitoring model. Wherefore, a synthetic data set is generated with one single diode model with shunt resistance in parallel at each irradiation and temperature level, taken into consideration a real meteorological profile for a typical year. This data set is then split into training data set to derive the optimal curve fitting and best architecture. Once we achieve a satisfactory performance, these models are tested with test data sets that own different patterns, ensuring that the model generalize well for unseen data set. Each model aims to predict 3 diagnosis indicators: power diagnosis indicator, voltage diagnosis indicator, and current, facilitating the fault identification stage. Regarding the dual stage monitoring model, it's based on 2-step methodology. Firstly, a projection function that aims to project the MPP from various temperatures, as seen by red and the blue, to the reference or standard temperature at 25 degrees Celsius. Actually, we enhance this projection function by creating a multiple polynomial regression model that take into consideration the relationship between temperature coefficient and temperature and irradiation. Then, once this projection is performed, the next step is to predict the diagnosis indicator. As seen, for example, for voltage in the state of the current taken based on the Spearman correlation, we segment the curve into 3 zones: high irradiation zone, low irradiation zone, and voltage irradiation zone, as seen by the zoomed figure. Since these methods are sensorless irradiation, the zones are taken with respect to the current magnitude, which exhibit a perfect correlation with the irradiation. For the second model, to eliminate the need for a projection function, we propose another monitoring model based on multiple polynomial regression. It integrates directly to the temperature as independent features. So again, as a relationship between voltage, the diagnosis indicator, and its independent variable is highly nonlinear, we simply segment the surface into 3 mini surfaces based on the temperature and current level. For the third model, we propose a more advanced strategy based on a neural network model. 3 independent neural network models are developed to map the relationship between the input features and the target variable. For simplicity's sake, to avoid deep neural network, we use a new independent variable for current diagnosis indicator with a logarithmic transformation to linearize the data set and to deal with the skewed data. The models are developed as follows. Firstly, as a data-driven model, require a large set of data set to achieve an optimal performance. We augment the data set using the fluctuation induced by the MPPT. Then, to prevent any feature dominating the learning process, we apply a normalization technique based on min-max technique. Then the data set are split using a hold-out technique into training and evaluation data set. Once achieve a satisfactory performance, the model are tested using unseen data set to make sure that generalize well for unseen situation. The fourth model is based on machine learning regression model. We perform a benchmarking process evaluating support vector regression, Gaussian process regression, decision tree regression, and ensemble trees using bagging and least square boosting. To enhance their prediction accuracy, we apply certain kernel function to map the input feature space to a higher dimensional space, facilitating the identification of fine pattern in the system. However, the performance under unseen dataset indicates that SVR, TR, and ETR exhibit high variance with decision. However, the GPR model, as seen by the bottom figure, achieve using matter, exponential, and rational quadratic kernel a higher accuracy with low variance. Their RMSE, their root mean square error, are below 5 for the 3 indicator power, voltage, and current. The final comparison indicate the effectiveness of the 4 proposed methods. All of them exhibit an MAPE, mean absolute percentage error, below 2%. So 2 models are selected for 2 distinct strategies. The selection criteria is based on the model complexity, degree of nonlinearity, prediction accuracy. Regarding the statistical model, MPR, multiple polynomial regression model, and dual stage, despite that the former exhibit a higher accuracy, it's excluded as it's based on higher nonlinear degree. So the dual stage is retained to be included in a stochastic filter owing to its lower nonlinearity degree. Regarding the data-driven model, the neural network is prioritized over the machine learning regression model due to its higher robustness. One of the main criteria of the diagnosis performance is to be able to adapt to different PV configuration and PV model manufacturing type. However, the model developed previously are tailored for a specific configuration and PV model type. They are more likely to fail if another configuration are applied or manufacturing PV model are under investigation. To deal with this issue, we propose a novel adaptable approach based on scalability and versatility. Scalability is achieved through a projection, a mapping function to map the new MPP using any configuration regarding the number of model in series and the number of model in parallel to the reference model through a normalization technique. The performance using a random configuration with 4 series and 2 parallel, it's worth noting that the reference configuration is 9 in series and 21 in parallel. The performance indicates the effectiveness of this method for the 3 diagnosis indicator. The percentage error is below 1E-3 for the 3 indicator, emphasizing their effectiveness. The other aspect is the ability of the monitoring model to adapt to various PV model type manufacturing. However, as you know, PV model type are characterized by unique internal parameters such as resistance in series and shunt resistance in parallel. This affect, as seen by the figure, the curve shape at ST at standard temperature. The second aspect, the response to temperature variation, is strongly dedicated by the temperature coefficient value. This temperature coefficient value varies between one model type and the another. So the main idea, we have to project the MPP displayed by the dashed blue line into the reference MPP displayed by the red dashed line, allowing to continuously monitor the PV system even if another model type is applied. To establish this relationship, given the nonlinearity of the IV curve, we need to firstly make a correlation tau2 between the dashed blue line and the solid blue line. Once this is established, a new relationship can be created between the solid blue line and red blue line. And as we developed previously a projection function based on the multiple polynomial regression function for temperature coefficient, we can now deduce the relationship between any new MPP for any model with the reference model. The effectiveness of this strategy is investigated using 3 panel manufacturers from MATLAB Simulink library, Trina, Hanwha, Canadian. The result indicate the effectiveness of this model to translate the new MPP for these 3 panels into the reference MPP. The MAPE, the mean absolute percentage error for the 3 indicator, current, voltage, and power is below 0.8. This is indicate the effectiveness of this method, allowing to use the already developed monitoring model without the need for recalibration or extensive data regeneration. Once the monitoring model are developed, the next step is to delve into the FDD strategy developed during this PhD thesis. 2 main FDD strategies are developed, as mentioned previously: hybrid strategy that target array level fault, and data-driven strategy. For data-driven strategy, 2 schemes are introduced based on neural network model, then a supervised scheme for scheme 1, and the stacking strategy to enhance the classification accuracy for scheme 2. The main objective is to enhance the robustness and sensitivity. Concerning the hybrid strategy, as we said, it targets array level fault modeled at the array side, mainly target open circuit fault modeled by ROC F01, series degradation modeled by RS F02, and shunt degradation modeled in parallel to the PV arrays that reflect potential end-use degradation. To replicate a real-world scenario, firstly, the MPP measurement and temperature according to some standard are doped with white Gaussian noises. These noisy measurements are then projected using the projection function to the standard temperature. Then, to restrain measurement noise and to ensure optimal estimation, even under stochastic environment, a bank of observer using Kalman filter algorithm is applied to decouple the 3 diagnosis indicator. These residual generation are then subjected to residual evaluation. The residual evaluation is done by using an adaptive threshold, which display a red solid line, and lower adaptive threshold by orange dashed line. To ensure that the reference diagnosis indicator is always aligned with the threshold, we propose a novel adaptive threshold based on the uncertainties of the regression model. Always given that the reference indicator display different characteristics and the profile at different irradiation zones, we propose to segment this threshold according to the current magnitude for high irradiation, low irradiation, and very low irradiation. Once these residuals are evaluated, the next step is to identify the type of fault in the PV system. This is done through a rule-based methodology. So firstly, we measure the IMPP, we dope them with noises, then we project this IMPP to the standard temperature. To avoid high complexity, we only predict the power reference diagnosis indicator. If the power reference indicator either exceed the upper threshold or breach the lower threshold, a fault alarm is generated indicating the presence of fault. Once this generated, the other 2 indicators are estimated, and if the 3 fault alarm are equal to 1, the fault identification strategy is launched. This fault identification strategy is based on either the reference indicator exceed the upper or lower threshold. It's actually based on the physical behavior of the PV system according to each type of fault. For example, if we have an open circuit in the PV system, the voltage will approach V open circuit while current drop to 0. It means that the voltage diagnosis indicator will drop to 0 while the threshold augment a little bit. As well as F03 soft short circuit exhibit two distinct profiles at low irradiation and high irradiation. Another condition is added based on the current magnitude to be able to distinguish between these two events. And finally, to avoid false alarm, it's worth noting that alarm delay is added to the system is based on the number of iterations of the Kalman filter need to converge to real measurement value, avoiding false alarm in the system. The final results are summarized through the confusion matrix. This confusion matrix is created by initiating each type of fault: open circuit, series degradation, shunt degradation, and short circuit at each irradiation and temperature level. Once these faults are generated, data are gathered and calculated. The confusion matrix allows to calculate the precision, the sensitivity, the specificity of this model. We can see that this model achieves a high accuracy of 19.16%. It achieved a perfect detection accuracy for healthy condition, short circuit, and open circuit, denoted by F00, F03, and F01. However, some instances are seen as shown by the red rectangle are identified as misclassification or false alarm in the PV system. This limitation are mainly due to the low power dissipation for series degradation, for example, at high irradiation due to low voltage drop, and for shunt degradation, especially at low irradiation level due to low power dissipation. To enhance this accuracy, we propose two other strategies, purely based on data-driven approach. The first strategy proposes a supervised scheme. So this strategy extends the classification granularity level to include model side, string side, and array side. Again, to replicate a real-world scenario, these measurements are doped by wide Gaussian noises, then injected into 3 independent neural networks to predict the diagnosis indicator. Then the residual vector are deduced from the discrepancy between the diagnosis indicator and the MPP measurement. For fault identification, all the reference diagnosis indicator, residual vector, and MPP measurement are injected into a supervised classifier scheme. A benchmarking process is conducting, comparing decision tree, support vector machine, naive Bayes, KNN, k-nearest neighbor, and some ensemble learning. To optimize the performance of this supervised classifier, a pre-processing step is conducted. Firstly, given the challenge or the nature of this data set, which is characterized by heterogeneous feature scale, nonlinear feature signature, measurement noise, and overlapping class region. Firstly, we remove the extreme data point without losing too much information using the maximum healthy threshold. Data balancing is achieved by a new hybrid method that combine undersampling and oversampling using adaptive synthetic generated point. For data normalization, we compare 3 main techniques: min, max, z-score, and Rob's scaling technique. At the end, for dimension reduction, we compare both feature selection using minimum redundancy, maximum relevance, and feature extraction using PCA. To avoid overfitting, data is partitioned using cross-validation technique. The overall performance of these data sets are shown by the heat map. These classifier, decision tree, naive Bayes, support vector machine, and some ensemble learning are evaluated step by step along the pre-processing chain to identify the contribution of each step. The raw data, firstly, we evaluate them against raw data, clean data, min, max, feature selection, and feature extraction. The code color indicate that the dark blue indicate the worst case, and the light yellow indicate the best performance. In general, we can see that the k-nearest neighbor and the bugging and random forest ensemble learning exhibits the highest performance. Based on this, we summarize this value into a general table indicated by 3 flags. A red flag indicates the worst case, and a yellow flag indicates a moderate performance, and the green flag indicates the best performance. From the analysis seen before, we can deduce that the no-parametric model, due to their flexibility to adapt more wisely to the data structure, achieve a better performance accuracy. It's seen, as we can see from the table, outlier removal and the class balancing are indispensable steps to improve the classification. Feature normalization is found to be indispensable for distance-based algorithm like k-nearest neighbor. Feature scaling perform better than feature extraction using linear transformation principal component analysis, but may lose some precision in the PV system classification. To deal with that, with this limited accuracy, we propose another method based on the stacking algorithm. The stacking paradigm, actually, it's based on 2 levels. Level 1, it combines a set of base learner, and level 2, and the decision is made by level 2 by a meta learner to improve the accuracy and reliability in the PV system. However, this model encounters some challenges, like what is the optimal number of the base learner, how to ensure diversity in the selection of the base learner, how to optimally guide the meta learner and to avoid this meta learner to access information from the base learner to give a realistic performance. To tackle this issue, actually, we propose another framework to best select the number of the base learner to ensure diversity and to guide the meta learner. So first of all, based on the supervised classifier, we select the top classifier with the highest F1, macro F1 score. Then from this macro F1 score, we identify the hard-to-learn classes based on the recall distribution from the confusion matrix. Then we can deduce the number of the base learner required. Then we select 2 optimized algorithms, 2 optimized classifier to identify their cost matrix to be specialized for a certain hard-to-learn classes. The selection criteria is based on many factors: the highest recall, the disagreement rate, the F1 score, and heterogeneous between the base learner. These base learner, the out of the prediction of these base learner are then fed into the meta learner. However, to guide this meta learner about the uncertainty of the model, we ensure the instead of feeding the meta learner with hard label like F00, F01, F02, we give the probabilities that give an insight about the uncertainty of each classes. Even though we found through simulation that this method is not enough. So to guide about the strengths of each base learner, we multiply the probability by the recall rate. And then the meta learner is validated under training using nested cross validation technique using the out of prediction. So firstly, we select the top classifier from the supervised scheme. It's identified, which have an accuracy F1 score about 0.84. Then we draw the recall distribution using the interquartile range based on the first interquartile range, which is marked in blue, which is equal to 0.71. We can identify the hard-to-learn classes based on the confusion matrix. It's F05, F09, and F10. So based on that, we select 2 optimizable classifiers based again on the supervised classifier scheme, the bugging and random forest. And we modify their cost matrix to be specialized for F05, F09, and F10. And based on the disagreement rate, the recall rate, and macro F1 score, we select the 3 base learner for the 3 hard-to-learn classes. Based on this criteria, we found that the bugging ensure the highest diversity disagreement with bug 113, which is specialized for F09, and RF12, which is specialized for F10. The result, after that, we combine the out of the prediction of these Bayes learners, 3 Bayes learner, we inject into the meta learner using nested cross-validation technique. We found that using this technique, it achieved a higher accuracy. The meta F1 score using the diverse algorithm achieved an accuracy above 99%. We can also see through the confusion matrix that there are equal distribution on the blue column. The recall rate for all classes are above 98%. Again, to emphasize the result of this, we draw the ROC curve, receiver operator curve, which give insight about the sensitivity and specificity of the model. We can see we achieve an AUC, area under curve, equal to 1 and superior performance than the Bayes learner. We can deduce that this algorithm, it's only meaningful if well architecture is explicitly constructed. As a comparison, in general, we developed 2 FDD strategy, a hybrid FDD strategy and data-driven strategy. The hybrid strategy ensure interpretability, adaptability, and robustness against measurement noises. It achieved an accuracy of 19.60%, but some limitation being observed, especially at low irradiation level. Considering the data-driven strategy, we developed 2 schemes. We expand the granularity level to include model, string, and array level. With the supervised scheme, the maximum accuracy is achieved using subspace K and N with an accuracy about 84%. Regarding the second scheme, we enhance and target hard-to-learn fault classes, and at the end, we achieve an accuracy of 99%. All in all, we establish a reliable, comprehensive, and scalable FDD framework. Through rigorous simulation results, these models indicate their robustness under challenging conditions. They enhance maintainability, availability, reliability in the PV system toward next step, proactive predictive maintenance. The contribution throughout or during this PhD thesis can be distributed either on the contribution side. We developed 4 monitoring models. We developed a new adaptable strategy to ensure that these monitoring models are able to generalize to different kinds of PV configuration and model type. Concerning the hybrid strategy, we developed 2 distinct strategies. The first, the hybrid strategy, we create a new combination that integrate the statistical data-driven model with model-based model based on a stochastic filter, and then a rule-based model knowledge derived from the physical behavior of the PV system. And then we propose a novel adaptive threshold. Concerning the data-driven strategy, we perform a benchmarking process, and we map the classifier robustness to each appropriate pre-processing configuration. For class-wise, we developed a new FDD framework to select the best Bayes learner, the optimal number of the Bayes learner, enhanced diversity, and probabilistic weighted diffusion technique. These contributions have been shared with international scientific community, mainly shared with in international conferences, webinar, and journal. As perspective, some papers are under review, mainly in the data-driven fault diagnosis strategy. We subject the supervised scheme and the stacking scheme, and also the adaptable approach. Despite this worthy contribution, this research work opened the avenues for further investigation. As a short term, we target to enhance the robustness and model adaptability of the developed FDD strategy. Regarding the hybrid strategy, we look forward to optimize the threshold design to even reveal incipient fault into the PV system. Regarding the data-driven strategy, we target to include, rather than principal component analysis, which is a linear method, we're gonna use a deep neural network based on autoencoder to improve the mapping from higher dimensional space to lower dimensional space. As a midterm, we will focus, or we will consider expanding the diagnostic scope to include physical and cyber fault, as well fault on the MPPT controller, power conversion unit, and sensor. We also consider to include a time series model like LSTM, long short-term memory, to capture the incipient fault in the PV system. And we look to share this data, this costly data, with other diagnosis community to facilitate and accelerate the development of diagnosis model in the PV system. As a long term, the main objective is to move from reactivity to proactivity in energy management by designing a proactive solution based on digital twin, predictive maintenance, and fault tolerance strategy, allowing to take the appropriate countermeasure action according to each type of fault, so make the microgrid more resilient and able to maximize the energy even under the presence of fault or failure. At the end, I would like to thank you for your attention and time.
Okay, thank you, Yehya, for your dynamic presentation and to respect the time spent for the defense.
Thank you.
So we will begin the discussion now.
Oui.
And we okay, if you want to drink something. And we will begin by the first reviewer, so Professor Jérôme Bosch.
Yes, thank you, Delphine, thank you, Chair. First of all, I would like to thank Adriana and Lionel for inviting me as a reviewer of this PhD defense. And also, I would like to congratulate Yehya for this presentation. I think it was really clear and also very pedagogical, also technical too. But I would like also to congratulate him for his report because sincerely I have rarely read such a comprehensive and detailed report concerning many aspects of energy. So it was really interesting, and I think it highlights the intensity of your work and also the depth of your study of the state of the art.
Thank you.
So thank you. So my first question concerning the state of the art, and in your presentation, I think it was slide 17, you talk about many points, if I understand, that I've not been taken into account concerning the uncertainties and also the dynamic of the MPPT. So can you clarify this point, please? Slide 17, yes. Yes, I think it's point 3 and 4, 2 and 3. Sorry. Research gaps.
The research gap?
Ah.
Actually, we found in the literature reviews that most of the FDD scheme using IV curve analysis, imaging technique, signal-based method overlook the system behavior actually in the low irradiation level and do not take into account when developed using MATLAB simulating the measurement noises. Neither the MPPT effect. They directly include, for example, a voltage, DC voltage side, and directly start to detect and identify fault. Hope I answered your question.
Mm-hmm. Yeah, okay, it's clear. Thank you. Concerning your physical model
Yep.
of the photovoltaic system, you mentioned to use a single diode model with a shunt resistance.
Exactly.
And I wonder how you identify the key parameters of this model.
Yeah.
Saturation current, for example.
Yeah, I'm looking for the comparison, just to make a comparison. Yeah, it's here. Actually, we make a universal comparison. It's based on 3 aspects: accuracy, computational complexity, and suitability for FDD. In the existing literature, there exists like 5 models, single diode model, with include only a current source with a single diode in parallel, this model is not accurate and not able to replicate the dynamic behavior of the PV system at different weather conditions. On the other side, regarding the single diode model with shunt resistance in parallel, can reflect both series degradation and shunt degradation, which is represented by the potential and use degradation, and have a lower computational cost. There is more accurate model based on double diode model in parallel. However, they have higher computational complexity and require careful choosing of the internal parameter of the PV model. So based on the single diode model, we found already developed in the MATLAB Simulink, and we exploited directly.
Okay, thank you. So my question regarding the data-driven models.
Yeah.
And more precisely, the multiple polynomial regression.
Yeah.
How did you address the issue of overfitting?
How we address the issue of overfitting?
Yeah.
Yeah.
Because if you...
Yeah, for sure, for sure. Actually, it's throwing this methodology. So first, we generate our synthetic data set using the one single diode model. We split this data set into training data, and we split another portion of this data set taken into expanding the range of this data set outside the range of the training set data set to ensure the model capability to generalize to unseen data set. We statistically ensure this low variance actually by measuring RMSE, percentage error, and MAPP.
Okay, so it is really a specific study for this type of system.
Can I have more detail? What do you mean?
So if you consider another photovoltaic system with over parameters?
No, these statistical parameters are applied everywhere to check if there is no overfitting in the system. Can be applied everywhere. This is universal statistical model, even can be applied in medical, for example, diagnostic process to ensure always there is low variance, or actually to make a balance between bias and variance.
Okay. So I have many questions, but I think I have to select my question. Concerning the Kalman filter,
yeah,
and the robustness of the hybrid model, so in your hybrid approach, your Kalman filter is used to adapt the system to environmental variation,
yep,
and also to reduce measurement noise. Could you explain how the filter parameters were selected or tuned in your study?
Yeah, actually for adapting the system to dynamic changing condition and attenuating the noise in the PV system, the Kalman filter first make a prediction using a state space model, normal state space model. Then to it include another covariance based on the measurement noises vector, usually denoted by V key, and the measurement noise and uncertainty of the model. These covariants are concatenated together to get the optimal estimation. So you are asking about R key and the Q key. This is the two main parameters to be tuned. And the initial parameter, the covariance matrix. The covariance matrix, according to the literature review, other article, mainly in vehicle to grid or vehicle, for example, sensor detection, they said that it should have high initial value, like about 10, if I remember well, to a quick convergence with the real measurement. Then the Q key and R key, honestly, it doesn't matter the exact value. The portion is the relation between these two, the percentage of Q key and R key. For example, if we give more weight to R key, it means we trust more the measurement. So as we need to diverge as much as possible from the measurement, we choose lower value for Q key.
Yeah. Thank you, it's clear. So now I have a question concerning the slide 21, please. So sorry, because I think it's
No,
classical
it's,
question.
it's a pleasure. No, take your time. 21?
20, yes, 21.
Yeah.
Yes. So the method is really clear, but here you mentioned in the second layer, the hidden layer, a number of neurons, which is 60. How do you choose 60 neurons?
It's an interesting question. Actually, up to now, so far in the literature review, there is no mathematical equation that based on the nature of the data can be described directly, the relation and how to take the number of the hidden layer and the number of neuron. So it's only based on testing, evaluating, training, many iteration to achieve the optimal number. But for example, we can have another method. For example, you can start with 10 neuron, with one hidden layer, with some activation function, for example, sigmoid, REU, LEU. Once you find, you have to analyze, for example, the training curve, the learning curve. Sorry, just 1 minute to explain better. What you can do, you can base, for example, you can start with five neuron and one hidden layer. You can analyze the learning curve. Is the training or converge with the validation curve? It's mean, it's good fitted. This model is suitable. If we found an elbow or something unusual or fluctuation, directly you have to increase the number of neuron. Or if the training curve decline with time, it's underfitting, so you have to augment the size of hidden layer and the neuron in the PV system. Otherwise, still up to now, in my modest opinion, there is no any mathematical definition that can use directly to define the number of neuron and hidden layer. But you can, for example, define the activation function in the hidden layer and the activation function in the output layer. And you can, for example, for us, we use a backpropagation algorithm based on marked Levenberg algorithm because it's the most suitable for noisy measurement.
Yes. Okay, I understand. I know that it is not so easy, but when I read the report, I thought, but I'm not sure that 60 is perhaps too much.
The MPP relationship is highly non-linear.
Because there is a lot of time for computation, and I thought perhaps there is a compromise between accuracy and the number of neurons. But okay, there is some good results, so it's specific to this model. But yes, I think it will be interesting to have more details about the number and the size of the model.
Yeah. Just to mention, I sacrifice a lot of time on developing this monitoring model, starting by 5, 10, 20, 30, go on. And even if you remember for the current diagnosis indicator, I was obliged to include the RMPP rather than voltage. So in doing a feature engineering and do a logarithmic transformation to linearize this data to avoid using a deep neural network.
I know. You did it with your own machine, or you have a specific computation systems in?
No, we start with this, and thanks to my supervisors, they purchase another PC able to perform this kind of problematics.
Okay. Okay, so concerning the hybrid model, the results show very high accuracy of the classification models. And specifically, thanks to the staking approach, how do you plan to answer the robustness and how to generalize this model to the real-world data?
The best solution is to experience our model, to evaluate our model with real data set. However, taking into consideration generating this faulty data set are very costly. But otherwise, we can, for example, generate a new type of the fault at different irradiation and temperature level not taken into consideration in the training and testing process, owing different pattern and outside the scope, the typical scope used. And in this way, we can at least ensure there is no overfitting and can be deployed in real scenarios.
Okay. In the beginning of your presentation, you explained that fault in photovoltaic systems, the impact of this fault was around 18.5% of energy lost. And so you improve existing method. So how do you evaluate your work according to this percentage?
Actually, as said at the end, this FDD strategy contribute to enhance availability, maintainability, and reliability in PV service lifetime. Actually, by developing this diagnosis strategy, it allows to timely detect and isolate fault. Once these faults are identified, the controller, the operator, as a next step, can take the appropriate countermeasure action, either, for example, isolating this faulty part, or ensure fail-safe to the system, ensuring resiliency of the microgrid at the same time. So it's maximize the return of investment. And for example, if it's only isolate this part, the energy management system have an idea about what's happening in the system and can take the appropriate measure, can forecast for the next 24 hours to take the optimal solution.
Okay, perhaps the last question. So your work, the aim of your work finally is to improve the efficiency of such photovoltaic systems. And in this work, of course, by using photovoltaic and renewable energy system. However, you need to develop your technique. You require a large amount of data, and also you need to make many calculation, computation, and perhaps sometimes it's to just gain a few percentage points of efficiency. So, in your opinion, could the carbon impact generated by all this data and calculation not act as a barrier of the large-scale deployment of such technique?
I fully agree with you. Regarding the data-driven method, it's only depend on the quality and the amount of the data set. And if another configuration, for example, are used, we lose a little bit of precision, specificity, and sensitivity in the PV system. However, for the monitoring model, firstly, we develop an adaptive strategy. This adaptive strategy allows to use different configuration and at the same time, different PV model manufacturing type. It allows to project directly the MPP from any PV panel to the new panel. And to complete actually the answer, we've developed two distinct strategies, the hybrid method and the data-driven method. The hybrid method is well suited actually for AC model topology inverter or string inverter. It can be applied at the array level and ensure high level. It doesn't require recalibration of the model, neither the regeneration of the extensive data set. It's based actually on the knowledge-based method. It's keep operator actually involved in the decision-making process based on the physical behavior of the PV system according to certain type of the fault. For example, if we take the example, if we have a short circuit in the PV system, this is physical, that the I short circuit will augment while V will diminish or will drop to zero. So taking into account that the diagnosis indicator is in a state of the current, it will augment to infinity, while the threshold, it's based on the voltage, will diminish, so we exceed the upper threshold. We are able always to identify this type of fault in the PV system. But for the data-driven strategy, I agree that we lose some precision and sensitivity using another type.
So thank you very much.
Thanks for you.
Congratulations.
Merci.
Thank you, Jérôme, for your questions. You have 3 minutes more if you want. Okay, maybe after. Okay, so Professor Astorga, it's your turn. If you have some comments and questions, please. Professor Astorga. Okay.
Yeah, we hear you.
Okay, thank you. Thank you very much. Je voudrais m'exprimer en français, si vous me permettez, parce que toutes les notes que j'ai prises, c'est dans français, si vous voulez, après.
Non, il n'y a pas de souci. Je vous en prie.
Ok, d'accord. D'abord, je voudrais remercier à l'Université de Bordeaux, spécialement à l'Institut technologique Estia et Adriana Aguilera pour l'invitation de participer comme rapporteur de la thèse de M. Yehya Al Rifai, qui a été dirigée par M. le professeur Lionel PQ et Madame Adriana Aguilera. Elle qui a une excellente collaboration avec les professeurs du Technologique national de Mexique, particulièrement avec les centres de recherche et développement technologique, brièvement connus comme CENIDET. Bon, aussi, je voudrais exprimer mes plus sincères félicitations à M. Al Rifai pour son travail.
Merci.
À mon avis, il a bien travaillé le fonctionnement des systèmes photovoltaïques, ce qui lui a permis de bien connaître les types de défauts les plus fréquents, les plus dangereux, les plus faciles et les plus difficiles à détecter. Aussi, il a bien révisé les méthodes existantes pour le diagnostic des défauts afin de détecter et localiser, identifier le type de défaut qui est présent dans le système. Les méthodes basées dans l'analyse des signaux, les méthodes basées dans les modèles du système et par l'analyse des données. Ici, je voudrais faire une petite pause afin de poser ma première question. Du point de vue économique, en prenant compte de la programmation, des capteurs, etc., à ton avis, quelle est la technologie que tu considères la plus avantageuse afin que le système photovoltaïque compte avec un système intégré qui soit utile à n'importe quelle personne, soit dans une maison, dans une entreprise, dans un hôpital, dans une école, de telle façon que l'information de ce système soit facile d'interpréter et connaître s'il existe un risque de panne imminent ou bien un faible risque qui peut facilement se résoudre.
Alors, votre question, c'était laquelle approche qui est le plus économique?
Voilà, du point de vue économique, quelle est la technologie que tu considères la plus avantageuse?
Mais basée sur le FDD méthode, les méthodes de diagnostic, ou sur les FDD approches? Parce qu'on a fait deux grandes comparaisons. Une entre les FDD approches, en comparant l'approche électrique, image analysis and visual inspection. Et après, on a fait une autre comparaison basée sur les différentes méthodes de FDD, méthode, signal, based model, knowledge based model, and data driven model. Non, pas encore. On n'a pas eu l'opportunité de faire ces tests-là. Mais c'est intéressant pour le futur. Oui, les défauts les plus importants par rapport à la Risk Analysis Review, c'est celle qu'on a utilisée dans notre système. on a considéré les défauts électriques, les mismatch faults et les défauts de dégradation anormale dans notre système. Les plus grands défauts, en fait, sont line-to-line fault, line-to-ground fault, and series degradation in the PV system. C'est en fait parce que ces défauts à faible irradiation, ils avaient une faible dissipation de puissance. Alors, ils restent toujours sur la puissance de détecter par les circuit breakers and the fuses. Oui. Oui, mais est-ce que oui, parce que à la fin, comme on a fait la comparaison entre les différentes méthodes, on a vu que le model-based method, elle perd son efficacité si le système il est très non linéaire. Comme vous le savez, l'équation dynamique du système photovoltaïque il est basée sur exponentielle. Et le current source est égal à exponentielle VT sur NK en tenant en compte temperature effect. Alors cette équation est très non linéaire. Elle requiert un filtre stochastique de type non linéaire comme un scented Kalman filter or particle filter. Deterministic observer, like, j'ai oublié le nom de ces observeurs-là, mais il a un deterministic gain, L. Alors, elle limite son efficacité. Alors que le Kalman filter, avec son Kalman gain, K, qui adapte facilement avec le change pour minimiser l'erreur entre les mesures et l'incertitude de modèle, il est plus adaptable. Alors, on ne pourrait pas utiliser l'équation dynamique de courant. On a créé une autre relation entre le MPP measurement, basé sur la puissance maximale à différentes irradiations et températures, et la relation avec les diagnosis indicators. J'espère que j'ai répondu à votre question. Merci. 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 J'apprécie votre opinion. Merci.
Okay, thank you, Professor Astorga. So you have at least 10 minutes more if you want to add some comments or questions. Okay, so we continue the discussion. Okay, please.
Thank you for the introductions. Thank you very much for your nice presentation.
Thank
you. First of all, I would like to congratulate for the quality of your presentation, the contributions to the PV area in the modeling and the detection of the faults. And also I would like to extend your congratulations to your supervisor, Ireland Adriana. And I have finished to say saying thank you for the invitation to participate in this panel, which I
Thanks
accept
for your presence.
with a pleasure. So thank you very much. Okay. Yes, in my opinion, the presentation was very nice, very clear. It was easy to follow the line of the contributions in your work. Also, the document that you have produced, the quality is very high. All the algorithms, all the techniques, all the methodologies are described with more detail. And what I say to PhD students when they finish the document of the dissertation is very important because it's your final point, but it's the start point from other students that are going to begin the PhD. So it's a good proof of the quality of your work. And it's the document support the contribution that you to your work. Okay, so okay, I totally agree with the contribution of this work to the PV foldation, as I said before. Also, I think the two great methodologies that you explained in the contribution. The first of it was the hybrid strategy and also the data-driven. Both of them with the advantage and disadvantage of depending of the type of the plan, depending of the data are available, or for example, depending of the quality of the data that you have. So both contributions, they are very strong in this area, so congratulations for that. About the publications derived from this thesis, I think the number of them are very suitable, very, it's okay. But I read that you have one chapter in 2023 and two conference Tripoli in 23 and 24, but in your slides 14 and 44, I saw more publication. Perhaps they are. You update the contribution, and it's okay because my comment was in the line that the document contains more contributions that you have published in the contribution that you have in the document. So my suggestion is that you follow submitting the result that you have obtained in your work, because many of them, I think they are not published in journals or in conference. So there are many results expecting to be published.
Thank you very much for your comments.
Okay, and now I'm just some comment about the scheme of the documents. For example, in the chapter 1, you provide a literature review of recent fault detection and diagnosis. But I think that the name of this chapter, is you say that there are literature review about microgrids. And I don't agree with that, because I think that the literature review that you have done is very well, it's perfect, but not only for microgrids. So it's for all applications, because the methodology is the same if you apply for a microgrid or whatever. So perhaps the name is not, if you see the name of the chapter, you expect more specific for microgrid, and it's not true, because the methodology is the same for many systems or energy systems you have. Okay, and in the chapter 2 is also very useful, because you have a review of fault detection in PV system. And also this chapter underscored the gaps in the lecture, and in order to get in value the contributions of your dissertation. Okay, in chapter 3, the microgrid taking as the case study is described, and you described the microgrid, but it takes my attention because I think you never use the microgrid. So you describe the macrogrid, but all the contributions are just in the isolate PV. So, okay, it's good, but why put attention in the whole microgrid and your contributions are just in the PV element? So, do you have any comment about it? Why did you include the description of the microgrid? Because when you are reading the document, I was expecting that you use the microgrid, but at the end, there is not in a whole context.
Actually, at the beginning of the PhD thesis, we start was, to be honest, we start with a target of energy and the proactive energy management solution for microgrid. So we start by developing the energy management solution, writing the optimization problem, and sizing the microgrid using a Hammer Pro analysis, and making as well a comparison between the different kind of battery or energy storage system. So we developed as well a methodology for the battery. It's under construction, under development yet. For example, we have developed the battery model based on the literature review as well, the Kalman filter, extended Kalman filter, and we propose an innovative method based on information theory using Kullback-Lever diversion. Yeah, Kullback-Lever diversions. It allowed to compare the covariance between the predicted and the measurement and to detect more incipient fault. As well, we have done a fault tree analysis identifying the different kind of fault in the PV system, drawing the fault tree and the cause effect we can find in the electrical vehicle and the energy storage system. So at the beginning, we target a microgrid, and then depend on the subject, we derive toward the diagnosis system in PV system. So even when I start reduction, I firstly include the battery system model. So that's why we have 2 chapter literature review for recent fault diagnosis and detection, and then a specified chapter with battery. But after discussion with my supervisor, it's found already the document, it's very heavy, yes, and it become very difficult to understand. So we exclude this part from the manuscript.
I agree that the document is very heavy in content, so yeah, you have to say stop until here.
Yeah, exactly.
Yes. Okay, thank you for your answer. Okay, you have used the Scenescape tool in MATLAB,
yeah,
to model with parameters to model the real plan, right?
The PV system.
This is the tool Scenescape.
Yeah,
it represents the real plan, and also the models that you are obtaining with your dissertation is just to estimate, right? But for the calculation of the residual, you compare the signals from the Scenescape tool and for your models, right? Okay. Yeah. So the model of in Scenescape with the parameters that you calculate at the beginning of your thesis never changes.
It changed because at the same time they are adopted with wide Gaussian noises, taking into account the uncertainties and the measurement noise according to some standard actually defined through IEEE and the International Energy Agency that specify the uncertainty of each electrical and measurement noises. We can see it here. And based on this, we calculate the Gaussian noises to create the uncertainty in our system. So accordingly, at each time step t, the diagnosis sampling time, the noises follow a bell shape. It's mean like normally distribution function.
Distribution format, more
Yeah.
or less, without.
Yeah, it's random.
Okay. My in the slide 13, you compare the computational chart from different strategies, but not. I didn't see in the document the computational chart for your proposal strategies. My insight, my reflection is about, okay, okay, this is the comparison for the computational chart, but in general from techniques, but not for your algorithm. Okay, so perhaps it was a good point to add the computational chart of all the strategies that you are proposed.
At the end.
At the end.
Yeah, yeah.
In order to compare, because the computational chart is very important in order to decide the model to use in a real plan. Okay, my insights or my reflection is about, okay, you are in an offline mode, you are obtaining the most suitable model of the plan, right? But in your future perspective, I'm thinking about to develop a digital twin.
What?
A digital twin.
Yeah.
In your future perspective.
It's the long-term perspective.
But the line of the estimation of the model that provides the estimation of the system is to integrate in a real time. So it's, what do you think about your methodologies that you propose, taking into account the computational chart, because you know that there is a adapting or the tuning process in order to adapting the model, because you have to change the model of the real plan that you are using in MATLAB. For example, the degradation, for example, the loss of productivity, some parameters that you have to update in order to obtain a good quality of your residuals. So what do you think about it?
It's a future direction for my work, actually. First of all, we have to develop the full microgrid, or at least it depends on the level of accuracy we need. So after that, we have to inject some disturbances like blackout, like line-to-line fault, and see the precision and the accuracy of our model. For real-time application, we have to make some recalibration according to real equipment. Then we can deploy this method in real-time strategy like Opal RT, hardware in the loop. I can, in real-time simulation, validate the accuracy and the robustness of this model. As well, the uncertainty of measurement through a communication protocol like Modbus, like AUC 6819. And in this case, we can ensure the reliability and robustness of our model before deployment in real-world scenario.
Thank you. And can you give us some estimation about the time that you need for obtaining a good model?
If you asked me 3 years ago about this question, I would like to tell you like 2 months, 3 months. But now I think I have already worked on the different type of the model in the microgrid in my recent work. So I think for it depends always on the accuracy and what we need exactly to investigate. But I think to develop the whole microgrid, I need 2 to 3 months as the whole microgrid.
Just the whole microgrid, just to update the model of the PV panel.
The PV panel?
For the PV panel also, to update the model with the new behavior of the system.
It will take less than 1 month for sure.
I mean, for example, in the slide, the 18.
18?
Yes. You represent the offline procedure, and where I I asking you is about this time, the offline process.
How much I spent? I already
More or
spent?
less, could you give us an estimation
Yeah.
about
I-
are days, are seconds, are minutes, or whatever, in order to
No, so for sure days
Okay,
and weeks, we can say months.
estimation.
Yeah, more than 6 months to develop all this monitoring model. And at takes time, the quality of the data, it's not easy to generate this type of the data through MATLAB Simulink, especially with an old PC. It takes too much time. And then we need to calibrate, we need to understand the nature of the data and how to separate the test data owing distinct pattern. So the procedure at the beginning, especially, I didn't have enough experience about the subject and take a little bit of time. But then I accelerate. And for the neural network model, the most models that take too much time.
Mm-hmm. Okay. I think when you are with the hybrid model, with the hybrid strategy, that you have the models with parameters, it's more easier to update the model, updating the parameters.
Yeah.
Perhaps in the machine learning methodology is longer, but in the model, the physics model, you can update the parameter depending of the discrepancy within the residual that you obtain.
But if you would like to ask me about this, I can easily 1 year to generate all this at the end to attain the objective and the performance of different classifier. The strength at each type, raw data, then I see the performance is not good enough. What can I do? I learn more about the pre-processing step. I do cleaning and balancing. I found in the literature it's not appropriate for our method. For example, we propose another method, understanding the nature and characteristic of our data. So we start, for example, with the cleaning. We will assume that any fault in the PV system exert a power losses on the power. So sorry, just a minute. So we propose our threshold based on the maximum healthy at maximum temperature and irradiation level. We trim this data. We don't use interquartile range, which is well known in the literature. So we get more statistical representation of our data set. Then once doing this, testing our model is not enough, then we do partitioning, class distribution partitioning in our data set. How we do it? At the same time, taking into consideration that the generation of these faulty data was very expensive and time consuming. So to not lose a lot of data, we need, for example, to trim the majority class like F05 and F06. We do firstly a hybrid method. Under sampling, we start by minimizing the sampling ratio of this, of the acquisition of this majority class. Then we propose an oversampling technique. At the end, we achieve an imbalance ratio of 1.3 to 1, so it's good. Then we propose, we have to understand the nature of the data and at the same time the characteristic of each algorithm. For example, distance-based algorithm is better suited with mean maximum strategy. So firstly, we do normalization. Gaussian naive Bayes is better suited with Z-score, and even more better actually with robust that deal with the outlier. Once to do that, to optimize the performance, the training time, also we suggest feature selection through, for example, minimum redundancy, maximum relevance, to eliminate the noisy and irrelevant feature from our data set. Then we take only the most relevant feature. Then we compared at the same time with another strategy based on PCA, principal component analysis. We found this strategy is not good at all, especially for such stochastic system with no linear behavior. So the time sacrificing for the data-driven method was huge, really.
Okay, thank you very much. Yes, my next question is about the computing of the thresholds in order to reject, in order to identify the false and also to reject the false. Could you explain with more detail how do you compute this adaptive threshold, for example? Do you select the operation of the plant? Do you select for the, for the threshold computing? How do you compute this range of the threshold? Because I think you take into consideration the operation of the plant and also the disturbance, but would you mind to explain with more detail and the frequency, for example, that you update this threshold?
So for the adaptive threshold, the first idea is to develop a threshold that follow and closely align with the diagnosis indicator, minimizing misdetection rate, but at the same time, minimize false alarm rate. So to take a balance between misdetection and the false alarm rate. We start by comparing the diagnosis indicator with the upper and lower threshold. How we develop our adaptive threshold is based on the uncertainties of the regression model. As we've seen before, the dual stage is composed of two steps. The first, a projection function from different temperature to the standard temperature. These projection functions have some uncertainty, have some estimation error. So we take into consideration as well, we see that as we segment the estimation function at 3 irradiation zones, the percentage error is different from irradiation to another irradiation. So we compare this by taking firstly mean percentage error for the whole system, for the whole uncertainty of the estimation model. We compare it against taking varying maximum percentage error based on only current level, and the other one based on the multi-zone statistical threshold, taken into consideration the temperature and the current. We found, for example, the method developed, which is displayed in a green dashed and solid line, are closely aligned with this threshold. This is validated through simulating using the Gaussian uncertainty and at each temperature and irradiation level to ensure there is no huge false alarm, or to have a balance between false alarm misdetection and good accuracy. So at the end, we achieve an accuracy at 90%, and this was our limit.
Okay, thank you. It's a good approach because it's very important, very relevant to set the threshold to detect the false. It's a crucial scope. Mrs. President, I believe I have one question mark. Okay, thank you. Okay, I'm going to select. Okay. Yes, about the degradation, in your dissertation, you set 6 operation conditions in order to simulate your algorithms, and you compare, you study the series degradation and also the chance degradation. But perhaps in the results, they are not clear how to differentiate when the degradation is due to series resistance or this fall is from the sham degradation. So can you explain that? I mean, you have 2 different cases of degradation, but I think in the real plan it's difficult to distinguish which type of fall. So how have you deal with this issue?
First of all, we have modeled the series degradation with a resistance in series. It actually reflects like aging degradation and the natural aging of the PV system. It reflects delamination, EVA discoloration, burn mark, junction box detachment, and cell crack. On the other hand, PID degradation, it's mainly represented with a shunt resistance is parallel. It represents the unintended circuit between the cells model and the frame. So we can, by adding another condition which take into account the earth leakage, we can differentiate between these 2 types of abnormal aging in our system, abnormal degradation. So it 2 different mechanisms. But the confusion it was between how to detect shunt degradation and short circuit. This is the most difficult case because both of them are modeled in parallel to the PV array.
Yes, I know that there are different mechanisms to occur, but the problem is how to detect and isolate the fault in both of them.
So that's why we developed lastly the stacking paradigm to target hard to learn fault classes. As seen before, for example, for the all-based learner developed previously, we can see all of them fail on the F05, F09, and F10, which describe cross-string, intra-string, short circuit, and as well shunt degradation. So we developed a new methodology, first of all, to select the best number of base learner, then ensure diversity. Then we specialize each base learner for a specific class only by doing some optimization, changing its cost matrix. So given more weight, for example, for F05. So this base learner is only specialized is expert only for F05. For any other classes, it can do anything. So for this case, for example, in our case, we take 3 base learner for each hard to learn class, and we do for the meta learner a weighted probabilistic fusion mechanism using the recall rate for each class. For example, at the end, if we take the base learner has a recall for F00 is equal to 0.97. We multiply by the probability. So the meta learner at the end have an idea about this algorithm, the strengths of this algorithm for F00, but no idea but for F05, it's not good. And in this case, we can improve the classification between shunt degradation and line-to-line short circuit, or cross-string short circuit, or intra-string short circuit.
Okay, thank you very much.
Thanks for you.
Okay, I have more questions, but it's time to stop because it's very interesting, your dissertation. So again, my congratulations for your work.
Thanks a lot.
Thank you for your good answer to my questions.
Thanks for you.
It's all. Thank you very much.
Thank you, Ascension. I know that the duration is short, but we have to keep the same time for all the people.
But we can discuss later.
Oh, of
Pleasure.
course.
Yeah.
Okay, we can stay here until midnight.
Yeah, no problem.
Okay.
I booked the whole week. So.
All the week. Okay, so we can let your current supervisor ask his questions, maybe, or add some comments. I don't remember the name of your supervisor from Schneider.
Jan.
Yes.
Jan, do you hear us?
Hello.
Yeah. Thank you very much. You mean the development of the full system, including the protection and the diagnosis part? Yeah. So first, to understand the nature of the different scale, we are talking about, we developed our model for low voltage side with DC voltage maximum 700 voltage, according to some standard and some standard. We respect the standard actually. But for the problematic, I think that's why I prefer to not give you an answer, because in medium voltage, there is lower current. In lower current, maybe we have to do some other transformation, feature engineering to be able to distinguish accurately the different type of the fault, because low power dissipation, and it's become harder, I think. Yeah. Thank you so much. Still, we have to finish our work firstly, then we can go for other one. I think after the thesis, I need some vacation. I need some day off now. Yeah, yeah. Thank you so much. Yeah, for sure. This is make me a little bit unsatisfied with the work done so far. Actually, the main idea as I develop an adaptable strategy for different PV model type, I was trying as well to develop another strategy. So said, this PV system has spent 1 year on the field. After 1 year, the resistance in series have dropped a little bit, increased a little bit. So the MPP point will be drift a little bit. So how we can continuously monitor even after aging without false alarm. I tried actually to generate this data using MATLAB Simulink. So by changing the resistance in series for the PV model, and I tried to describe this relationship between PV model after 1 year, 2 years, 3 years. But the relationship, it's highly nonlinear, and I cannot describe it by a simple polynomial regression like second order or 3 order. And when we have to do the correlation between the MPP at different temperature and reference MPP, the problematic is very complex. So maybe I have to use an LSTM model, long short-term memory model, to include it with our strategy. In this case, we can keep monitor our system even after certain years of operation. Yeah. Thanks for your presence. Thanks a lot.
Okay, thank you. So it's my turn. Okay, I have some questions and some comments. So first of all, I would like to thank Lionel and Adriana for your kind invitation for this jury. Thank you, Yehya. It was very nice for me to observe your evolution also.
Thanks.
Since your master internship.
It's been a while.
Yes, it was very nice to see that you become a researcher with very good skills in and knowledge in IA for PV instrumentation. So, of course, it's a little bit difficult to finish the jury because most of the questions have been already asked for you. But maybe I have only some questions and comments about the work in order to complete the discussion. Maybe about the data. So I have questions about the temperature measurement of the data. If you can explain me which temperature you take into account into your model. It's the temperature of the junction, the ambient temperature, or anything else? And do you have any thermal model associated to your electrical modeling?
Actually, it's a very interesting question. Thank you very much. I took the ambient temperature.
Sorry,
but I took ambient temperature based on some research work done previously on the ambient temperature. For sure, there is, for example, a thesis on the PV system fault analysis using IV curve measurement. They assume as well the ambient temperature as a cell temperature. They said, according to some standard, there will be 2 to 3 degree differences. It depends on the irradiation level and the type of fault as well. And they assume. But for example, if we develop a robust thermal models that take the relationship, the correlation between the ambient temperature and the thermal temperature, our work will be valid with a cell temperature.
Yes, because as you know, the ambient temperature is okay to be taken into account around the MPP, but for too low or too high temperature, of course, the model is not a good one.
Exactly.
So maybe you, comparing to the complexity of your modeling for finding any faults, I think a thermal model working in parallel with your electrical modeling is not so hard to include. But okay, so
but we will consider that for future direction.
Okay. I wonder why you don't speak about the thermal modeling in the prospects. Maybe I have another question about threshold. Okay, so you have heard the discussion with Ascension, but how could you help engineers to choose the right thresholds. If you imagine the translation of your work into concrete project, real projects, how could you help engineers to find, to define, to use any thresholds at the end of your work?
Yeah, actually, it's a very interesting question and big question at the same time. Because before developing any threshold, we have to understand the complexity and the nature of the system itself, and how we can play to ensure that this threshold closely align with the indicators that we need to supervise, to monitor, and to avoid false and missing alarm. So as we can see, for example, taking a binary classification problem, when we have the null hypothesis and the alternative hypothesis, the main interest is how to choose our threshold so that minimize the type 1 error and minimize the type 2 error. It depends, for example, if we take, for example, medical cases. For example, detecting there is a disease is not so important, but for some other type of issues, we have to detect at early stage. So we can accept more false alarm in our system, but we have to detect. If there is not, we can do another test study. After that, there is a lot of statistical method depending on the system. For example, p-test, chi-square test, z-square test, ANOVA test. For example, this statistical method work well for medical purpose because the data are less nonlinear depending on the age, on the pressure, on the blood, for example. But for our model, for example, if we take the wind turbine, for example, or the batteries, the system is highly nonlinear. So for this stochastic systems, the development will be, we need to use, for example, optimization to optimize, for example, the Euclidean distance between the adaptive threshold and the indicator. Otherwise, it becomes very difficult.
So your advice is to let the system, imagine you arrive on the real PV farms, okay, of 1 megawatt, okay. Your advice is to let the system be observed, monitored during different months.
In this case, for PV, yeah.
And you define the threshold from what you have observed?
It's not only depend on the model itself. It also depends on the accuracy of our model, physical model. So both of them we need. First, we have to observe the generation of the data. It take like, depending for day-night transition, it's enough. To take the irradiation, for example, or 1 week, it's more than enough. Then we check with this data the accuracy of our mathematical model developed. If, for example, need some calibration, we can add an epsilon that describe the error between our model and the new error to avoid this kind of false alarm in our system.
Okay, so it concerns better works done with simulation before any implementation.
Yeah.
Okay.
Or otherwise, we can go for a real-time simulation study like HEL, like hardware in the loop.
Okay.
And we can test it also with a full system integrating HMI, integrating real controller, integrating protection system to...
Okay. I wonder about the state of the art, because I have studied about the same approach, but for fuel cell and batteries. Okay. So I wonder if you have seen works in the state of the art ensuring the reliability of the system from the DC-DC converter. Did you see anything, any work about the detection of any fault on the PV farm from the DC-DC converter?
For PV system or for battery?
PV system.
For PV system.
Because some works exist with batteries and fuel cell.
Okay.
In fact, we inject high frequency signal from the DC-DC converter in order to exit the system, okay, and take the information from an analysis of the signal. Okay. Do you see anything else with PV system?
No, I'm sorry, I didn't see
no?
any, because we focus more on the PV array side. and we didn't see. Most of them are focusing, to be honest, on imaging analysis technique based on thermography. They are based also on exciting, for example, the model with
Yes, I
infrared
understand.
camera to have to examine the discrepancy about thermal anomalies between the PV cell, or for example, luminescence technique as well to excite the system by applying a forward bias voltage to detect the emitted light by the cell and the discrepancy between them. Most of them right now are focusing on IV curve analysis on the DC side, on the PV array side, and the imaging technique.
Okay. It was only a question of curiosity.
No, but it's a good
which
question.
comes
Maybe I have to look for other, because for example, when we start the research, we focus on
Don't worry. It
one
comes
direction.
during the defense, so I didn't have time to check it also. Maybe a last question regarding the implementation for real-time problems. So I wonder what could be the good compromise between performance of the algorithm of detection and robustness. It means take into account of uncertainties on measurements, sensors, and so on. So do you have any idea about this compromise? So how could you accept to reduce the rate of performance in order to be more robust against the measurements? So what could be, in fact, the threshold of performance for you? Because 99%, of course, is a very good rate of performance, but you can be sure that it will not be reached for a real system.
For sure, with a data-driven model.
Exactly. So what could be a good level of performance taking into account of...
for real life?
Yes, for you.
For real life?
Yes, real life, yes.
And the data scientist and machine learning engineer, they consider above 80%, it's good enough.
80?
80%.
Okay.
It's more than good. And there is another strategy right now. For example, once we develop this, the next step is to add a self-training strategy. So with evolving over time at each iteration or at certain period, we adapt the model and let them train selfly with the data at each time. So at the end, about 2 to 3 months, because we start with 80 or 70%, for example, and then at the end of 2-3 months, we can go up to 90% again.
Okay.
And this is very interesting in our research study.
So it means that you could reduce the complexity of the algorithm, the model, and so on, in order to be more in coherence with the standard of detection. Okay. Maybe a new prospect for you.
Yeah, for sure.
And I have one last question. So it's a general question.
Yeah.
As a chairman or a chairwoman. I have 3 questions for you, but you can choose one between the 3. So number 1, number 2, and number 3.
Number 2. I like middle.
Number 2. It's more difficult.
I know. I should.
No. How could you position your work in the local state of the art? So you have worked during the 3 years in the lab, in a team. Okay. So how can you what is the position of your work into the local state of the art?
What do you mean position? For example, it's if we have...
You arrive, you are not a Superman, okay? You don't begin your work without any data, any knowledge, any skills, any colleagues. So how could you position your work into the state of the art? Because it's a common mistake for a PhD student to write a report forgetting to explaining the local state of the art. How the idea comes to begin this project. Okay, what are the skills of your supervisor with this project? How these ideas come into this team?
Actually, this idea comes with time. As we said previously, we start the state of the art on proactive energy management. We start to develop a fault-tolerant strategy. We found some gap, for example, in battery detection. At the beginning, there is another researcher called Carlos Bordon, for example, who developed some fault-tolerant strategy based on some typical fault in the microgrid. So we start to follow this. At the end, we focus or we think about adding a contribution in the fault identification and detection strategy. We delve into this, and I found myself in the ocean. Yeah, but at the beginning it was very terrible. I think I didn't find myself. I did a lot of mistake, and I learned at the end from this mistake. But yeah, even choosing the right, the appropriate article, it was for me a challenge as well.
Okay, thank you, Yehya. Do you have any questions to complete? Assumption, yes. No, not at all. Est-ce qu'il y a un docteur parmi vous qui souhaiterait poser une question? Non plus. Okay. So we will finish with your supervisors. So maybe Adriana? Oh, Adriana, you have to say something.
You can say it in French.
Okay, thank you very much. I would like to thank Yehya for your hard work during all this time. We worked together, and I think we learned together a lot of things. You show me and you help me to improve in research skills, but also with supervisory skills.
It's too much.
Thank you very much. I would like to the members of jury to accept our invitation here. Jerome and Carlos, the reviewers, you were in my earliest stage of my career, so means to me a lot of to have you and to have your advice in the Yehya work. Thank you very much. And Ascension and Delphine, thank you very much for your way to Basque Country and to give your very, very experience, a lot of experience and your opinion and your advice in this presentation and the work of Yehya. I am pretty sure that in your work you will done very well, and I express my congratulations and my thank you again for
Thanks a lot.
all that we
Appreciate.
Share together. And thank you to Lionel for your collaboration, for trust in me in this first supervision. And yeah, thank you very much to the public to come today and share with us the joy with Yehya, and all the best.
Thanks a lot. Thanks.
I will keep the microphone on. So it's my turn to thank also. I will take this opportunity to thank the member of the jury as I join Adriana, Jerome, and Carlos. Thank you for your time. We all agree that it's a hard PhD, so not so easy, this task, I imagine. Thank you for your time. Thank you, Ascension and Delphine. Thank you, Delphine, for kindly accepting to be chair. And thank you also, Jan, for I think it's very important for Yehya, your presence today, even in online. And I'll take this opportunity also to say some words about Yehya. When Yehya started this PhD, I must admit that it took a little while for him to find his orbit around the topic. We had some slow takeoff, as you mentioned, a few detours. That's why also this discussion about the microgrid. But once he finally got into motion, let's just say that we had the hard time to stop him. I think you so also today, when he starts, it's not easy to stop him. So from that point on, his energy, curiosity, and determination become unstoppable. Simulation never stopped running till the last moment he made one more, and always full of idea and progress. So beyond the technical contribution, what stands out most is the transformation I've seen. The person who began this journey a few years ago is not the same person that stay in front of you today. Has grown into an independent researcher, as you can see today, full of insight and persistence. So here, I would like also to congratulate you, not only for completing your PhD, but also for becoming part of that special group of people who know exactly how to make a simple problem and look extremely complicated. And then solve it. So we are proud of you. Huh?
Thank you very much.
Thank you.
Okay, so it's the end of the jury, so we have to get somewhere, okay, for the discussion, and we will come back here just after. Okay? Thank you.